Right, good afternoon, everyone, and thank you for joining me for the final day of APIs Revisited, part of Digital Leaders Week. And in today's API Hour, I'm joined by Mark Jose, Technical Principal at Scott Logic. If you have a question for Mark, pop it into the question box and we'll take as many as we can at the end. And if you've missed any of the other API hours taking place this week, you can access all of the recordings on the Scott Logic website, and I'll put the web address in the chat box for you shortly. You'll also be able to download the white paper that accompanies this webinar series by clicking the same URL in the chat box or by filling in your survey at the end. Now, if you've watched any of the previous API hours this week, you'll know that we're using our surveys to support a very good cause. Throughout Digital Leaders Week, Scott Logic is donating £5 to the Altitude Foundation for every completed survey. The survey takes just 60 seconds to complete, and I'll give you more information about how to access this and tell you a bit about the charity after Mark's presentation. And we'll be able to see at the end just how much money we've managed to raise. So let me now introduce you to today's speaker. Mark Jose is a technical principal with more than 20 years of software development experience. He's developed software in most languages and is a consultant, developer, and architect. He's developed and architected solutions in the investment banking, energy trading, and gaming sectors, including a number of trading platforms. He has a wealth of experience in cloud technologies, most recently evangelizing strategies that avoid lift and shift cloud migrations. When he's not writing software, he can mostly be found under the bonnet of a car, trying to figure out how he broke it. So without any further delay, let me pass you over to Mark.
Thank you, Claire. Thanks for that introduction. Welcome, everybody. So today, I guess I'm going to be talking about building modern web APIs. I guess what do I mean by modern? Well, in order to talk about modern, I'm going to have to cover a little bit of the past, a little bit of where we are now, and today I'm going to try and predict the future a little bit as well. However, I guess there's a few disclaimers around this. I've told to keep this talk not too technical. So if there's technical people on the call and I sound a bit too condescending, then sorry about that. There's some technical concepts that do need to be understood to cover some of the ground I'm going to cover. So I'll try to keep them as high level as I possibly can. If you want to talk to me about some of the technical detail, then reach out. I could talk about this stuff all day. I'm quite passionate about it, so do reach out. Some of the stuff in here is my own opinion, I guess, especially when we get to the future part. Please don't pin anything on this. This is my thoughts about what the future looks like. Definitely not Nostradamus or anybody like that. I'd like to start with application programming interface, and if you followed my colleagues' talks for all of this week, they've probably covered this, what is an API. So I'm really going to quickly skirt over it, and actually it's a way of defining interactions between systems. They generally tend to define the type, the method, the data format, and any conventions of the interaction, but most of all they define modularity, and this is what Wikipedia has to say about APIs. Let's start in the past. If we go, we're talking about web APIs specifically in this talk, and web APIs, by web APIs we mean APIs over the World Wide Web, WWW as it was called years ago, and these days the web, the internet gets out there interchangeable terms. They shouldn't be, but they are. There's a few little concepts about the web that we really want to understand, and in a way I guess the World Wide Web is an API. You ask for something and the server gives you it. That's a request and a response with some content. And the contract for that's quite well defined. So a lot of these web APIs I talk about are going to use a lot of those concepts. And in order to understand those, we have to understand some of the terminology. Again, this is the part where you probably know some of this stuff. We're going to use terminologies like URL, you've probably heard of, which stands for a Universal Resource Locator. That's the www.google.com. whatever. That you actually type in your address. When you actually make a request, files and content are transmitted over the internet using the hypertext transfer protocol. That's where the HTTP comes from, and HTTPS these days is prolific, secure Hypertext Transfer Protocol. So let's talk a little bit about the World Wide Web. Way back when the World Wide Web came about, and you could ask for a file, you could ask for a video, you could ask for a sound, you could ask for images, you could ask for content over the internet. So you would say, give me some content. You'd give it a URL, a universal resource locator, and it would work out from that address where that content lived and send you the content back. And then we talked about, I've just signposted the Hypertext Transfer Protocol. That's a definition. Hypertext Transfer Protocol 1.0 was around back then, and that's the protocol that allows you to send the files back over the internet. In 1996, Roy Fielding started work on HTTP 1.1. While he was producing that, he produced his PhD dissertation called Architectural Styles and the Design of Network-Based Software Architectures, which he published in 2000. And basically that talked about a concept called representational state transfer. That's easy for me to say. Otherwise known as REST from here on in. And basically what he'd said was pretty much what I've just alluded to, that the internet is a way of asking for things over the internet and getting things back using HTTP. And that didn't have to be files. It didn't have to be images. It could actually be information in some format. SOAP was a thing back then, an example of that type of information coming backwards and forwards. And these days, RESTful interfaces tend to use things like JSON and other file formats. There's actually a specification around REST, or some definitions around REST, and it's based on 6 principles for RESTful APIs. All RESTful APIs are basically client-service architecture. So the principle behind the client-server constraints is the separation of concerns, and separating the user interface concerns from the data storage concerns improves the portability of the user interfaces across multiple platforms. It also improves scalability by simplifying the server components. But perhaps the most significant to the web is that the separation allows the components to evolve independently, and then that supports internet scale requirement of multiple organizational domains. So that's the client service architecture that a RESTful interface would need. They're stateless. They have this statelessness. The client server communication is constrained by no client context being stored on the server between requests. And each request from any client contains all the information necessary to service the request, and the session state is held in the client. So the session state can be transferred by the server to another service, for example, a database, to maintain a persistent state for a period and allow authentication. I guess number 3, cacheability. So as on the World Wide Web, clients and intermediaries can cache responses, and responses must implicitly or explicitly define themselves as either cacheable or non-cacheable to prevent clients from providing stale or inappropriate data in response to further requests. And well-managed caching partially or completely eliminates some client-server interactions, so that further improves scalability and performance. REST defines a layered system. So a client can't ordinarily tell whether it's connected directly to the end server or to an intermediary along the way. So if a proxy or a load balancer, for example, is placed in between the client and server, it won't affect the communications, and there won't be a need to update the client or server code. Intermediary servers can improve system scalability by enabling load balancing and providing shared caches. So also security can be added as a layer on top of the web services, and then clearly separate business logic from security logic. Adding security as a separate layer enforces security policies. But finally, it means that the server can call multiple and other servers to generate a response to the client. Code on demand is optional, and servers can temporarily extend or customize the functionality of a client by transferring executable code. For example, compiled components such as Java applets, client-side scripts such as JavaScript type. The final one I want to cover in a bit more detail. So most people who produce REST interfaces tend to adhere to most of that stuff. There's not many people doing that much code on demand generally these days, but people do it. But REST defines that you must have a uniform interface, and the uniform interface constraint is fundamental to the design of any RESTful system because it simplifies and decouples the architecture, which enables each part to evolve independently. And the 4 constraints for this uniform interface are that you have resource identification in the requests, resource manipulation through representations, self-descriptive messages, and some people may have heard the term HATIOS, so Hypermedia as the engine of application state. Now, all of the things in white I've had on the previous slides are things that people tend to consider when building RESTful interfaces. However, Hypermedia as the engine of application state is the one that's always missed in my experience. And that's why when people talk about a RESTful interface, I like to refer to interfaces that people describe as RESTful as more like REST-like interfaces. So let's, I'll come on to what HATIOS is in a bit, but let's talk about the two types of operations that REST-like interfaces tend to support. And I'm going to cover the least used case first. So I guess REST-like interfaces support resources that invoke operations. So I guess what I'm going to do here is I'm going to show you some examples of requests. And as this is a non-technical talk, when you see a monospaced font that looks like code, it's not code. It's just a font I picked. But there is some understanding. I suppose that's a little bit necessary before I talk about these things. So as part of the hypertext transfer protocol, when you make a request to a server, you have to give it a few things. You have to give it, you need a universal resource locator, a URL, which tells it where that resource lives on the internet. And you also use a thing called a verb or a method, sometimes they're called. And there's a number of really commonly used verbs. So get, post, put, patch, delete. Generally, these allude to get, I want something from you. Post, I'm giving you something new. Put, I want to change something in its completeness, in its entirety. Patch, I want to change part of something. Delete, I want to remove something. So those are the commonly used ones. There are others, there's options and a few others, but those are the most common ones. And actually, to be fair, in a lot of RESTful interfaces, get and post are the most commonly used. Whenever you ask for a website, for example, when you type www.google.com into your browser, that's essentially a get, and you're asking Google for content. When you get a response back, that response normally has a body. It's the information. That might be a file. It might be an image. With a RESTful API, it's generally some form of JSON document, which is a JavaScript object notation file. And the other thing you get back is you're going to get back a status code, and that status code will indicate to you a little bit about what happened at the server. Some common ones that you might have seen. If you've been playing with WebSockets, you might have seen 101. That's an escalation. 200 generally means everything was fine and it worked, and here's some data back. 202 is I got your request and I'm dealing with it. So some of these 302, 308 are redirections, permanent or temporary. 400, 404. Everybody's familiar with 404, page not found. So 400 is an error on your part, and 500. So let me summarize. 418 I've got in brackets actually. 418 is an interesting one. 418 is I'm a teapot, and there's an interesting story between I'm a teapot. If we have time at the end, ask me about it, and I'll tell you the story if you don't already know it. But I'm going to rattle through because I'm quite limited for time. I guess as a general rule, in these numbers, anything in the 100, hey, here's a thing, some info, it's an information response. 200, you're awesome, well done. What you asked me to do, I did. Team, go team. 300, it's somebody else's problem, generally redirections. 400, you're an idiot, you sent me a bad request. 500, I'm an idiot, I broke when you sent me the request. So they fall into 5 real categories. So now we've got the verbs, I guess, sorted, and we've got the responses sorted. Let's look at a request. So this is a request that might invoke an operation. It's a post, which means I'm going to send some data. So I'm going to send some data to this URI. So it's a speaker's database, maybe, where I want to register as a speaker. I'm going to send my information, which is that request body in the middle. And I'm going to get 202 back. Now, 200 means okay. 202 means accepted. And what this means is I got your request, and I'm going to go off and do something, and I may complete that at some time in the future. Now, obviously, with registration, with modern systems, you'd expect that to be quite quick. You'd expect that to be quite quick. Let me give you a more concrete example. Imagine it was something like this. So API servers rust.com, some cluster, create a VM. That's going to take a while. Now, with a RESTful interface, there's no way of the server telling you when it's finished. What you'd have to do then is you'd have to say, are you done yet? are you done yet? Almost like when you go on a long drive with your kids in the car. If anybody's got kids will know this. Are you there yet? Are you there yet? It's really annoying. There's no way for the server to say, I'm done with that now, you can continue. Generally with operation requests that invoke operations, the verbs map onto these applications. So if you post something, it's generally to invoke an operation or to kick off a job. If you do get something, it's to retrieve the status of an operation that's already ongoing, and delete is to cancel operation. And they map quite nicely actually onto what I'm going to talk about next, which is resources that manipulate data. Resources that manipulate data, if you've ever looked at a RESTful, REST-like interface, you'll be familiar with these sorts of things. The sorts of things they say are, here we go. So this is the same example I had before, except instead of a registration this time, I just want to post myself as a speaker. Now that's something on the other end, it's probably going to stick me in a database somewhere, and it can do that very, very quickly, and it can come back and give me a 200. Okay, I did that. I took the speaker record that you give me, and I put it in a database. And with these types of resources that manipulate data, the address addresses the resource itself, normally a protocol followed by a domain followed by some path to that resource. And these types of, so actually let me go back. Say I've got speakers in the URL here. I'm not addressing an actual speaker, I'm addressing speakers as a collection. And I guess with REST you have two types of paths. You have a path to a collection of things, a collection of resources, and you have a path to the resource itself. So with that in mind, if you use these verbs with a collection, for example, so if you post, it'll generally create a resource, get will list resources. Put and patch are not that regularly used against collections. With resources, generally you won't post to a resource because you'd normally patch to replace or patch to partially update or put to replace and get to get. So these are the most commonly used actions for resources and collections. So let me, I mentioned before, I mentioned Hatio, so let me talk a little bit about that. If I do a get, so I'm saying give me all speakers here, the response is going to be a list of speakers. Now I've only put one on this slide because I'm assuming there's only one speaker you ever want to listen to. It's me, obviously. When it comes back, I might have a sub-resource of talks. So these are the talks I've done. Now, in a lot of REST-like interfaces that we see regularly, this talks list is a list of IDs of talks. It's not the full URL, but REST says that you should have the full URL because then the client doesn't need to know anything about the location of resources to then go and get that resource. And this is the bit that's neglected, and this is the reason why I tell people a lot of their interfaces are REST-like. So this is a collection of speakers. So it gives me a list. This, if I want a particular speaker, then I can say speakers with an ID. And if I say, there's different ways of structuring this data. So I could say my talks are here. So it's speakers 1 talks. And I could also say that actually you could go and get talks and get a list of just the talks. And this is how you could progress through the system. So you ask for a thing, it gives you some data and a list of URLs to other things that you might be interested in. You can then go and request the other things. So on, so forth. One funny thing is the REST spec actually says you should have a reference to yourself. I don't think I see very many REST-like interfaces these days, which have a link to themselves. So I guess that's REST. So REST's really, really cool. And actually the majority of all web APIs that you find these days will be RESTful, REST-like over HTTP. They're great, and they're generally well thought through when they're public APIs. If you want to know about public APIs and other APIs, then let me signpost you back to some of the other talks earlier in the week. Graham kicked off on Monday and talked about different types of APIs. When they're public, they're reasonably well thought through generally. I guess the only problem is when you want to use an API as a client, you have to ask for everything. So if I say, give me speaker Mark, I have no way of telling it to give me small bits and bobs. So how do we fix that? Well, welcome to 2012 if you worked for Facebook. If you didn't work for Facebook, welcome to 2015 when GraphQL became the GraphQL Foundation and it was made public. Made public in 2015, actually became the foundation in 2018. And GraphQL was an internal project at Facebook, which allowed the Facebook app, if you like, to just request the information it needed. So it's described, I guess, as a query language for your API. So if you think back to the examples we've just looked at and then compare it with something like this. So what we're saying here is we're making a post, but the post is actually a GET because we're posting some information to the server. So we still follow the HTTP standard. We're posting a request that says, I would like a speaker. And in that speaker, I would like name, job title, company, and Twitter. And the response is a speaker with the name, the job title, the company, and Twitter. Now, that's very similar to a RESTful interface. A RESTful interface might have given me all of that stuff in the response back, and I might not have to send a request and just change the verb to a GET verb. But the thing is, with GraphQL, what I can actually do is I can do that. So I can say, give me the speaker name. And all I get back is the speaker name. On the back end, excuse me. On the back end, that's exactly the same record in the database or in some other system. However, I've told the API what I would actually like. And it's interesting, I kind of like to think of this as the a la carte menu to what was the set menu for REST. And I did come up with that analogy, and I mentioned it to one of my colleagues here, and he said, actually, it's the other way around. And he's totally ruined that analogy for me because what he said made a lot of sense. I'm not going to cover it now. So we can request the individual bits. We can also say, actually, I want talks YouTube link. So I would like the YouTube link out of all my talks. And what it'll do is it'll give me the speaker. It'll give me my name because I asked for it. It'll give me my talks, but instead of giving me all the information about my talks, it'll just give me the YouTube for my talks. Notice the shameless plug. They're all worth watching, by the way. The other thing you get with GraphQL is when you want to talk about a RESTful API, it describes the way you send the message, the way you receive the message, the payload, but it doesn't tell you about the content of the payload so much. GraphQL includes a full type system, so you can define the payload. And again, I don't want to get too technical here, but these are essentially what I'm saying here is, if I ask for a speaker, I can definitely expect the speaker to have a name, a job title, a company, a Twitter, and an array of talks, a list of talks. And likewise for the query, I can ask for speakers queries, and likewise for each talk, I can ask for a name, or I can ask for a YouTube link, or whatever. The good thing about this is it lets the outside world know what they're allowed to ask for from your API. I can add to that. So I want to add Vimeo link as well as YouTube link. I can add to that. So this allows for evolution of the API. It allows for API versioning. And likewise, if I wanted to remove YouTube because I didn't like it, I could deprecate that. That would let the outside world know to anything that they knew that they develop, or soon, I'm going to get rid of YouTube links, so stop using it. And then by doing clever analytics around the number of requests that are being made, you can see who's still using it and who's not, and you can start sending out emails to say, look, you should deprecate this, you should remove this out of your software. And you can also track it, so when nobody's used it within a month maybe, then you can remove it completely. So it allows for safe removal of properties and safe versioning of your APIs. That's all great. I want to digress a little bit, because what I'd like to do is I'd like to talk a little bit about how some of these APIs are backed. So you generally have a client calling an API. An API has to get that data from somewhere. And these days, a lot of organizations are moving to microservices style architectures. I don't want to go into microservices. That's a completely separate talk and quite a long one at that. But what I'd like to do is I'd like to give some examples here of the sorts of APIs that you see. So an API might be quite simple for the example that we've had. So on an API, you've got some speaker service, you've got a talk service. They're both backed by the same database. You might have a speaker service and talk service backed by separate databases. You might have speakers and talks backed by separate databases, but speakers talking across the talks talking across the speakers. Obviously, these sorts of combinations are sometimes bad practice, but not stuff that we haven't seen before. You might have routes where the speakers talks to the talk service and the talk talks to the speaker service. I guess the point is you don't know what's going on behind this API. You might have something way more complex and starts multiplying up. And I'd like to think about what actually happens here when you make a request to an API. So if I ask for something from an API, that request has to filter all the way down the chain to get the information I need from the guts, from the very bottom. And then once each of those things have been requested, it's got to filter back up the chain in terms of a response. And at each point where you merge two responses, you've got to wait for a little bit, We're going to have to wait at this point, and we're going to have to wait at the speakers for both of the other dependency services to merge back up to the API to send a response out. And actually, in some cases, you can hang around for waiting for a long time because you don't know what's happening behind the service that you requested. The speaker service, for all we know, might be the API has no concept of what's behind the speaker service. So that's microservices, and I'm heading towards something. I'm taking you on a little bit of a journey. So I'm going to leave microservices for a second, but I want you to bear in mind what I've just said there. I also want to talk about a little bit about documentation because it ties into this. Once you start building these APIs, GraphQL allows you to do some documentation, but it's not great developer documentation. You've got a type system. You can look at what types exist, but there's no real human readable text that tells you how to use this thing. And actually, I want to start with an example of some of the projects I've come into as a consultant and seen how documentation is being done. And I don't know whether this is the same in your organizations or you've seen it in other organizations, but what tends to happen is this sort of timeline where somebody comes up with some requirements for your API, and then your development team go away and implement that. They build an API, and at some point, somebody between the code and the API stage realizes that we need some documents for this. We need to document how this API is going to work. So when we start selling it to people, people need to know what's going on. So what they do is they write some documents and they put them in some portal. Now, when I say portal, I use that in the loosest sense of the term. In the past, it's been normally in some sort of WYSIWYG type editor, like Confluence, for example, or creating the docs normally becomes a manual task, which doesn't get any resourcing. And documents get out of sync with the code in your API very, very quickly. It's a disjointed approach. And actually, to be fair, in a lot of these cases, developers aren't probably really the correct people to do the work. They shouldn't probably be writing documentation. There's no concept of consistent specification there. I've drawn spec on this diagram because I think I'm being a little bit unfair saying there's no spec. Sometimes there is a spec for these things. So I'm going to go back a few years, step into the breach, Swagger. You've possibly heard of Swagger. You may not have heard of Swagger. Swagger was a library that used to auto-produce documentation for your APIs based on some syntax that you would put in your code when you wrote your code. And that was the then. I guess that brings me nicely into the now, which is the middle part of my talk. In this part, I guess Swagger has evolved into OpenAPI, or the OpenAPI initiative. I don't know if you've heard of OpenAPI. I'd imagine if you've written any RESTful interface or played a part in it, you probably have. And Swagger documents have become OpenAPI documents, and it's now an adopted standard. Version 3.03 is the latest version. And what OpenAPI allows you to do is define your APIs in a technical fashion. So you document first. The OpenAPI spec was donated to the Linux Foundation under the OpenAPI initiative in 2015. And this spec creates a RESTful interface for easy developing and consuming an API by effectively mapping all the resources and operations associated with it. So it lets you build the API document in a way that code can understand. So you document first, and that changes your flow. Your flow ends up looking more like this. So you do some analysis about what the API needs to be. You write your OpenAPI spec, which can be your requirements. Like, you don't have to come up with requirements and a spec. The spec is written in a human readable language. It's a JSON file, so you need to understand JSON. But it's a well-structured document that allows you to write in human readable text. And also allows for all sorts of constructs that allow you to reference other specs and things like that. And then what you can do then is, from that spec, you generate your document and your code simultaneously. So your documents and your code are always in sync. And actually, to be fair, a lot of the tooling now that's evolved around OpenAPI, you can automate a lot of that. So there's tools now that will fully automate your documents and your developer portal, which allows you to test APIs and all sorts of stuff. That's completely all automated. From your code, the code step, to your API can be automated. And actually, you can even use your spec to generate the boilerplate for your code. So your development teams can actually take the spec, run an application against the spec, and it will generate all of the boilerplate for the code. So all of the big blocks, if you like, and all they need to do then is plump them out. Because these specs perform a really common document, what you can do is you might have multiple teams within an organization. And if you decide across your organization as a standard, we are going to adopt the OpenAPI specification, then your specs become your organizational digital blueprint for your APIs, essentially a town plan for all of your APIs. If you manage them in a central repository, you can allow teams to function where they can see other teams' APIs, and you don't duplicate APIs, and teams can use each other's functionality. So that's a bit about documentation. I'd like to talk a little bit about, because we're in the now, we talked before about if you ask a RESTful API to do something and it doesn't do it immediately, then you have to keep asking, is it done yet? Is it done yet? There's no way of the API telling you when it's finished. We're seeing a bit of a change in thinking, and actually, in the world's become a now place. People are very impatient. If you order something online, you can normally always do it before like 10 o'clock at night. You can have it the next day, and actually, in some of the big cities, you can have stuff within an hour. Like, the world is a very impatient place. RESTful is a little bit like micromanagement. It's like, have you done that yet? Have you done that yet? Have you done that yet? And versus like non-RESTful, asynchronous, which is empowering people. Go in, do a thing, and come back and tell me when you're finished. I'm going to put up a slide of buzzwords. These are all buzzwords in the web API space that you've probably heard mentioned. If you're a technical person, you'll probably know what a lot of them mean. But they all allude to one thing. They allude to asynchronous requests and responses. Actually, not even requests and responses, I guess, asynchronous APIs. I say not requests and responses because actually responses can be unsolicited, i.e. not asked for. People can just send stuff to you. And when you take what we looked at before, that microservices type architecture, we're moving away from that. Everything goes down the pipe to the leaves of the tree, and then they all come back up to the branch to come back as a response. We're moving to these sort of these flows, if you like. So a request comes in, and it'll pass through the flow where the request will be modified, or it'll modify things as it passes through, and then some outcome will be pushed out of the other end. This is quite a simple example of the flow I talked about before, where you request a speaker, it finds the speaker out of your speaker's database. It might then enrich your speaker object with your talks for that speaker and then push it out. They're still two separate services. There's still a speaker service and a talk service, but the way they're arranged are in a different way, and they push that out. You might get more complex flows like this. I mean, flows can come in, they can branch and they can rejoin, and you can get some quite complex flows. You can also get reference data from some of the RESTful type APIs that live around your flow, if you like. If we think about the old request response thing, what we'd have to do if we use this type of architecture with a request response, you'd have to have this route somewhere, i.e. when it's finished, it has to be able to give you the response. And you don't know how long that's going to take. It might take a while. So enter streaming APIs. I know we're in the now, but I want to allude to, we do a lot of work in finance, and I want to allude to something that came about in 1992, which was FIX, the Financial Information Exchange Format. And this was a protocol that was designed to facilitate the transport, or the efficient transport, of messages between back-end financial trading systems over, at the time, a network, a TCP, for the technical people in the call. It came about in 1992 as part of a document published called the Electronic Communication of Equity Trading between Fidelity Investments and Salomon Brothers, and it was by a guy called Robert Lamoureux and Chris Morstatt. And FIX has evolved and evolved and evolved, but they had the right idea. I mean, they said, actually, not everything is a request and a response. I might want to tell you something, but actually, as the client, I might want to, as the server, I might want to tell the client something without the client asking for it. And we've got that tech now in web technology. So we've got WebSockets, we've got HTTP2, which is kind of getting there, and we've got long polling and polling. Now, long polling and polling are a bit of a cheat. WebSocket truly this bidirectional transport. Long polling and polling, I'm not going to explain what they are now. You can look them up, but pretty much it's a kind of make a request and leave the request open so the server can throw things down it until the request times out, and then make another long request. And that's pretty much how they work. The reason why WebSocket hasn't been a thing until recently is, well, WebSocket could be a thing on-premise. Let's take the on-premise case first. Most systems look like this. They're a client, they're an API, and then there's your backend system, whatever your system is. And if that's all that's on premise, you can literally talk from your client to your API in any way you choose, because you're not going to be constrained by InfoSec or any of your organizational security or network arrangements. Generally, that's not exactly the case in large organizations, which are quite siloed. But when you move that onto the internet, the chances are your API and your system are going to be in the cloud or on the internet somewhere, and your client is going to be on a premise somewhere. And to get there, it's going to have to go through a firewall. Now, making requests and responses through HTTP is easy, because no organization in their right mind could close a firewall to those types of requests. Otherwise, the internet or the web wouldn't work. None of your staff would be able to get to any website in your browser. So the reason why HTTPS worked in that field is because it uses the same mechanisms to make those requests. WebSocket not so much. However, it is becoming more and more prevalent as more streaming media comes about. More security, network security principles within organizations are having to consider allowing WebSockets through. Now, managing a WebSocket and keeping it alive and letting it die and stuff is actually quite a big thing. Actually building a piece of software that is resilient using WebSocket is quite a big thing over the internet. The internet is a flaky place. So there are a couple of libraries that people tend to go to these days. SignalR on the left there, and gRPC. I'm not going to cover them. You can have a look at them yourself. But what I would say is, if you're going to do WebSocket, don't build it yourself. So I want to quickly cover documentation, and I want to move into the future. So documentation, we kind of said OpenAPI was the standard for defining RESTful documentation. A while ago, back in 2016, someone raised this issue. I'm not going to show the actual issue, but you can grab that link and go to it if you want. On the OpenAPI spec GitHub page, where OpenAPI managed their spec, and it asked the question: can we use OpenAPI, the OpenAPI spec to specify a streaming API? There's a lot of debate. There's actually 4 years of debate, and the last post was a few weeks ago in that issue. The general consensus was no, and OpenAPI have been avoiding doing it. So enter async API, and async API is very, very similar to OpenAPI in that it follows a lot of the same principles, but it's for asynchronous or streaming APIs. So that's where we are now. A lot of people are looking at streaming. A lot of people are doing REST, even though it's REST-like and not RESTful. What do we see as the future? So I'm going to go back to a little slide I had a few seconds ago. Most systems we build are your system, which is hosted somewhere. These days, a lot of it's either on-premise, private cloud, or public cloud. It's somewhere on the internet. The API is your connector block between the internet and you. I also want to remind you of the very first slide I brought up. So the very first slide I brought up said, I wanted to get my speaker record from api.conference.com. If you think about where that fits into the slide I just had, the client is going to make that request and expect that response. If this was a post and I was posting my information, I'm sending my information to the system, the database in the system is probably going to have a different schema to that, or it's going to maybe have different field names, or it might pass through multiple systems. So we might have something on if I make that request on the left there from the client to the API might be asking the system, it might be calling a function in the system called getSpeaker1 and returning a speaker object, where things are slightly different. But if you think about what your API is doing here, all it's doing is just mapping data. And APIs generally do one of three things. They either map data, so they map it from one format to another, or they merge data together, two requests into one or whatever, or they split stuff and send it off to multiple services in the back. That tends to be the three operations they do. So if we call our API a mapper, then is there something we can do about that? A lot of new systems, greenfield systems that we're looking at the moment are cloud native. They're being built in the cloud. The three big clouds, I guess, Azure, AWS, and Google. My most recent experience is with Google, so I'm going to talk about Google Cloud Platform a little bit here. A few weeks ago, I gave a talk called All About the Base, another shameless plug, by the way, which is backend as a service. And I guess I didn't want to do the slides again, so I'm going to steal a couple of slides from that talk. When I did that talk, I talked about these are the things that you generally want from a system. And actually, the things that you actually care about are these 4 things. And if we look at those 4 things, they're pretty similar to the slides I've used previously in this talk. So there's some storage, there's some logic, there's an API, and there's the client, which is the UI. So taking the concept I talked about earlier and saying there's a store, there's some logic, your API is essentially a mapping layer, and then there's your client. What if we could have the vendor of the cloud platform give you your mapper and your store? They're generally going to give you a store anyway. It's not very often you're going to go and build your own database. You're going to pick some tech. And in a lot of cases, Azure, you might use AWS, you might use API Gateway, for example. In Google Cloud, you might use Apigee or Cloud Function endpoints or something like that to give you a mapper. So what if you could do that? So not so long ago, Google realized that if you break down a universal resource locator, a URL, you have this protocol piece at the start, you have a domain, which is the organization, if you like, and then you have a path, a bit in purple, a bit in pink here, which alludes to the resource. So I'm saying I'm looking for talk number 4 for speaker number 1. So that's just an address, and it doesn't really matter how you break that down in software. It's still just an address of something. And if you think about a file system, it's pretty much like a file. So if I go into the folder speakers and look for document 1, if document 1 if I could have a folder within my document 1 has a folder called talks, and talks has a talk called 4. Then what I can actually do is I can represent this. And what we're saying is the URL looks very much like the path to an item in a database. So I said I was going to talk about GCP, the logo on the left there, but Google Cloud Platform launched a product a good few years ago called Firebase. Now, I'm not going to cover Firebase. I could, again, reach out to me. I'll talk about Firebase. I'm blue in the face. I think it's a fantastic product. But Firebase has a database which was originally released for Firebase called Firestore. It was originally called Real-Time Database, actually. And then Firestore's incarnation. And then Firestore was pulled into GCP and is now available in Google Cloud Platform away from Firebase as a product. But what it does is it's a database that contains data, how you'd expect to store it in a file system. So you have collections, and collections will have documents, and documents can have collections, and collections have documents. Now, if we go back to what I was originally saying, that format is very, very similar. So what if your API goes away? What if you could just talk to that database straight over the internet? You can talk to that database straight over the internet, and the database will receive something. Now, anybody who's worked with Google Cloud Platform will realize that what you can do is you can trigger off Firestore databases, so you can trigger off multiple things. So what I could say is, if I want to send my request, I can remove my API, use the Google API, and actually write some data into speakers, speaker 1, talks, talk 4. And I can write this exactly the same data. The action of writing that data can trigger an onCreate function, Google Cloud function, and that cloud function can go off and do something and write data back into the database. If I take that approach, then essentially I've flipped our understanding of a system a little bit on its head, because basically what we've got is we've got our client, we've got a vendor SDK, which is our API, we've got the store immediately after there. You'd expect the business logic to come between there, and your store facilitates the logic. I'm not going to go any further with that because I'd like to invite questions about it. That's my prediction of the future a little bit. Thank you. I've been Mark, and if Claire's about, I'm sure she'll pick up at this point.